Okay, so I think first I'll talk about in the second part the result that sometimes you need a non-conembeddable M to couple things optimally, even if you start with something that's from matrices. And to go back to George's analogy of comparing this to the Hausdorff distance, right? And like trying to, I'm going to formulate this in a slightly different way, right? So
Didn't quite hear what you said.
So you mentioned like this idea of the Gromov-Hausdorff distance, where you embed the metric spaces into a bigger metric space. Right. So I'm going to talk about the coupling distance here in a slightly different way. So let's say given mu and nu, then let's say suppose that you take A to be the von Neumann algebra generated by some x, where x has the distribution of mu, and B to be the von Neumann algebra generated by y. And so then if you had a coupling, and let me call the coupling x prime and y prime to distinguish it from this x and y, right? So I'm taking these as a given algebra, and then if I had a coupling, then that would be some other, like a copy of this x, right? So this would be the same distribution. Right. So then the von Neumann algebra of x would be isomorphic to the von Neumann algebra of x prime because they have the same distribution. Similarly for y and y prime. And so then, and so in other words, you get embeddings of trace preserving, in fact.
So if you have a mu, then there is an x prime. There is an x prime that has no fit on it.
Right. So this is because, as I mentioned, the GNS construction and allows you to build such.
Which construction?
The GNS construction.
Oh. Okay. Okay.
Yeah. I mean, there's some subtlety to that, but I mentioned that before. But anyway.
This is relevant, but I never refer to it as a GNS construction because I don't know what S is. This construction is in the paper of Bill Fenton and Meinberg, which is years before receiving those papers.
Okay.
Maybe it was on a different side of the ocean.
Okay. Anyway, though.
Want someone to give me an explanation.
Unfortunately, I was not there, so I cannot explain why it was called GNS construction. Anyway, yeah. If you have a coupling, then you get embeddings of this A and B into M. Right, and so then you can also formulate this Wasserstein distance. Right. So in fact, maybe I'll write this in the following way. The Wasserstein distance of the law of x and the law of y as the infimum of alpha of x minus beta of y, where you have alpha and beta being trace preserving embeddings into some M. Now, another fact that I'll use here is that, well, if you're looking at the L2 distance of x and y, so x and y, the distributions of x and y are fixed. And so in particular, the L2 norm of x and the L2 norm of y are fixed. And so then to find the distance between x and y, what really matters is the inner product between x and y, right? Because the because you expand in your Hilbert space. Oh, wait, this is real anyway. Okay. All right, you expand out the inner product, and you see, well, so this would be an L2 of M with its trace. And this here, L2 norm of alpha of X is just the same as the L2 norm of X, and this is the beta of Y. L2 norm is the same as L2 norm of Y. And so these things are fixed. And the only thing that's changing is the inner product. And so in this sense here, then you could say that this Wasserstein distance is the L2 norm of X plus the L2 norm of Y minus the sup of the inner product of alpha of X and beta of Y in L2, where you have the alpha and beta as above. So this formulation here is useful because it allows us to make a connection with the so-called factorizable maps. Okay, so I'm going to erase this. All right, this page here was just saying, okay, I can rewrite this as instead of thinking of distributions, I could, if I want to think about in terms of von Neumann algebras A and B generated by X and Y, I could just consider possible embeddings of A and B into some M, and then try to make the image of X and the image of Y close together. Right, but then when you write it, when you do this second trick of writing it in terms of inner product, right, and you have your alpha, in fact, maybe write it like so, alpha from A into M and beta from B into M, right? And then if you're looking at the inner product of alpha X and beta Y in L2 of M, I'm leaving the trace implicit here, right? But the L2 depends on the trace. And if it's a factor, the trace is unique in it. But this alpha of X and beta of Y, you could rewrite it as by taking the adjoint of beta. Right, so you could consider the adjoint beta star, which is the conditional expectation, the unique trace preserving conditional expectation from M onto B. And so alpha composed with beta star, this is what is known as a factorizable completely positive map. Right, having a factorization as a trace preserving star homomorphism followed by a trace preserving conditional expectation. So this is from the work of Claire and Tharman de la Roche, which indeed did this in a more general setting that was not necessarily tracial, that considered type 3, right? So actually you can consider also like modular automorphisms and whatever. But here in the tracial case, this is just what the definition is, that say phi, capital Phi, from A to B, called factorizable if there exists some M and trace preserving.
I think the name of Annette Ferrando de la Roche is even more syllables than you got on.
Oh yeah, I guess I forgot this. Okay, but you can't read this anyway, so it's fine. So factorizable maps is defined that, yeah, there exists alpha and beta such that this phi is exactly this beta star alpha. Yeah, and so this idea, I mean, this is all very elementary, but it gave us a good insight that, okay, we were studying this optimal coupling problem and free probability, but now if we translate it in this way, now we can look at what do people know about factorizable maps. And there's quite a lot of results about this.
What is phi? Do we have a phi?
Phi is a sorry. Yeah, so this is a motivated these factorizable maps arise in the context of quantum information.
Well,
right? So when you talk about a quantum channel, so a quantum channel from A to B is a unital, completely positive, space preserving map. And it's typical in quantum information theory that you consider some kind of thing like this. So for instance, to be a very nice examples of this would be, say you take A and B to be matrices, and then you take M to be like a matrices, I don't know, tensor sum traceable to Norman algebra. So it could be like the hyperfinite R that comes up in many examples, right? And so then you could think of this, so you could define alpha from MNC into M. You could define it by alpha is equal to, basically just mapping it, taking something and tensoring it by 1, and then conjugating it by a unitary. So actually, maybe make this alpha of x is x tensor 1 conjugated by some unitary. Right, so you could take some u, which is a unitary of MNC tensor R. And so then this is a quantum channel that you get is you're taking your matrices, embedding it into you're tensoring on this auxiliary space. Then you're doing a unitary rotation, and then you're taking the conditional expectation back down. Right, and this is an example of a factorizable map because you can take alpha to be the inclusion followed by the unitary rotation, and then take beta to be the conditional expectation.
okay, but this is a factorizable map because it's constructed from a factorization.
Yeah. So then, there's a question of like what maps are like. Are all maps factorizable? The answer is no, they're not. But it took some work to prove that, right? Because in quantum information, people tend to like use this as their main example, and like they don't.
What's the advantage of being factorized? How do you notice?
Well, I don't know. I mean, I guess it's just like something like this is easy to work with. And actually, if you're dealing with matrix algebra, right, and if it is factorizable, well, if you have two copies of matrix algebra inside a 2-1 factor, they're unitarily conjugate. So for a matrix algebra, having some decomposition like this is sort of almost equivalent to being factorizable.
And then Ross must have some reason to talk about factorizable maps.
Yeah. So there's lots of connections. I think what I will stick with is Hargrove and Mushat showing this connection to the Kahn embedding problem.
To which?
To the Kahn embedding problem.
Oh, I'm getting
Yeah. So I'm not an expert in quantum information theory, and perhaps someone else can say more about that at some point. But so anyway, well, so you can have different classes of factorizable maps, right? So you can consider factorizable maps. Well, so you consider, say, unitary, completely positive, and trace preserving maps. So let's say maps. So we're from MNC to MNC. Unitary, completely positive, and trace preserving. Right, and then we have the factorizable. And these are not, there's a strict containment here. And one example that shows the strict containment is a map, which is a convex combination of the identity map and the transpose map. So there's certain, so there's certain values of the coefficients in the convex combination that'll make it be unitary, completely positive, and trace preserving, but not factorizable. And in terms of factorizable maps, there's also ones, one instance of a factorizable map is if you replace this with a commutative algebra, which would basically mean that your map was a convex combination of unitary conjugations or automorphisms of n by n matrices. So you could have the convex hull of automorphisms of matrices. As I said, the automorphisms of matrices are all given by unitary conjugation, and you can take convex combinations of those, and all those will be factorizable, but there's actually a big difference between this and all factorizable maps. So for I don't remember what exactly, but definitely above 3, above size 3, above n equals 3, these are different. I think this is true above n equals 2 as well. Okay, so those are factorizable. Then you have ones that are factorizable through through something that's finite dimensional. And so here, if you take factorizable through finite dimensional algebra, right, meaning that you can take the M to be finite dimensional, then this is okay, so the closure of this closure, right, is the same as factorizable through con-embeddable. So I don't know, you probably have heard about the con-embedding problem, like whether any tracial von Neumann algebra embeds into ultra product of R. It's another version of that is saying embeds into ultra product of matrices. And basically the question is whether, and another equivalent formulation is, can any non-commutative distribution be approximated in weak star topology by the non-commutative distributions of matrices? And okay, so Hargrove and Mushat showed that these things are that the closure of this is this, and they also showed that the con-embedding problem is equivalent to saying that whether the factorizable things through finite dimensional closure is equal to all the factorizable maps. And so in particular, given the announced negative solution, that would imply that these things are not equal to each other for a certain n. So saying that there are maps which you can factorize using some m, which is not con-embeddable, but which cannot be factorized using con-embeddable m. And so then if you take these results and do a little bit of argument, which I think for the sake of time, I'm not going to go into detail, but so a corollary of all these considerations, which which is in a joint paper with of me with Gangbo, Nam, and Sliaktenko, is that negative solution to Kahn embedding implies that there exists say some, so there exists N and D and some D tuples X and Y of self-adjoint matrices, right, such that such that the Wasserstein distance between the law of X and the law of Y requires a non-Kahn embeddable M to realize. So if you only use Kahn embeddable M, you'll get a strictly larger estimate for the distance. Yeah. Well, this I don't directly. It's not a proof that says suppose there exists some M which is not Kahn embeddable, then I'll construct this. Right. The proof is if there's a negative solution to the Kahn embedding problem, then these spaces are distinct. Consider a factorizable map that doesn't factorize through Kahn embeddable. Then you use some kind of duality argument with the vector space to come up with X and Y that will so the X and Y will kind of witness the difference between your factorizable thing that's doesn't factorize through Kahn embeddable versus this, right? So it's actually like a hyperplane separation argument. You take your factorizable map that's separated from the closure of the FM fin. You find a separating hyperplane, and then using some duality, you express the separating hyperplane as taking some tuples X and Y and applying C to the tuple of X and taking the inner product of Y. And then this tells you that.
X and Y optimally, the optimally contained in the same C.
So I'm switching. So I'm looking at the formulation of optimal coupling, like I said at the beginning of the second half, right? Where the copy. So the things that are going to be optimally coupled are some X prime and Y prime, which are copies of X and Y.
Are you still talking about optimal transport?
Yeah.
And then where does that come into this further? If I may, where do you have are X and Y? Is that an optimal presentation?
So the optimal coupling will be a copy X prime and a copy Y prime of X and Y. That will be in some von Neumann algebra M, which is not Kahn embeddable.
Is that related to the corollary?
Yeah. So in the corollary, I have X and Y.
Yeah.
Such that to find an optimal coupling of the law of X and Y, right? So if I make a coupling of the law of X and Y, that means that there will be a copy X prime and a copy Y prime of X and Y in some app.
I don't see where it's written anything about optimal coupling. And that's bottom line.
Yeah, because I ran out of space. Okay, so the statement is that so that the soup of, let's say, phi in the factorizable map, phi of X and Y, is strictly bigger than the soup over the phi that comes from the Kahn embeddable of X and Y. And so in particular, that implies, right, that the infimum of alpha of x minus beta of y, where you consider alpha embedding from matrices into M, right? And M, which is con-embeddable. This is a so for the con-embeddable version, this distance is strictly bigger than the distance that you would get for M, which is not necessarily con-embeddable, right? So you have the same thing here, but M arbitrary.
So I forgot that you were going to be using the inner product.
Yeah.
And that's where the factorization comes in.
Yeah. Right. So this argument here gives you something about this inner product, right? And then this converts to saying something about the Wasserstein distance.
Okay, so, and this somehow is included in the last line.
Yeah. Okay. So I'm trying to expand
Yeah.
in more detail
Okay.
because I ran out of space there. So I tried to write it very succinctly, but this is a statement that you get. And then this tells you something about the Wasserstein distance as well, right? That if you only use con-embeddable von Neumann algebra, then you get a strictly bigger estimate of the distance. And yeah, so this is kind of weird. Like, okay, think about classical probability, right? Imagine you have finite dimensional commutative space, right? Then it's just a finite set. And if you try to take couplings probability measures that are finitely supported, well, they're supported on the product of the finite sets, right? So you can always find optimal couplings of the finitely supported measures that in a discrete space. But in the non-commutative case, this is the opposite. You can take your individual distributions to come from the matrix algebra, right? So it's analogous to like discrete probability distributions, finitely supported. But in order to have optimal coupling, you need to use non-con-embeddable von Neumann algebra. Right? And this is also like very different than the non-commutative case. Right? In the commutative case, you have, I mean, all measures can be approximated by finitely supported measures. Right? And then you could argue that some analog of that statement in the non-commutative case would be trying to say that any non-commutative probability distribution could be approximated by ones that come from finite dimensional algebras. Right? And that is equivalent to the con-embedding problem, which, as far as we know from the recent work, is false. So, in the non-commutative case, you have this failure of finite dimensional approximation, and this failure of finite dimensional approximation also affects the computation of the optimal coupling distance.
That's all very interesting. I'm having a little trouble keeping track of it. And so what does the corollary say again? What is its significance?
Says the negative solution of the con-embedding problem implies these statements here. That there exists, certain n and d and x and y such that these have strict inequalities.
Okay. And where does the optimal coupling come in? I'm not quite, didn't quite see that here.
Well, choosing so the coupling here is encoded through the alpha and beta and the m.
Yeah.
So an optimal one here, that would mean like one that achieves this infimum.
But okay, so we're assuming we're taking it for granted that there always exists an optimal coupling.
Yeah, it exists. Yeah.
Okay. And how does that help deny the well, first of all, we're assuming that, assuming we're trying to prove the quantum embedding problem, that we.
Oh, I'm not trying to prove the
No,
quantum embedding.
you say a negative, solution, that implies something, but that's, but we, okay, so, but then the idea is that's what we have, the negative solution.
Yeah.
But then, so also the right-hand side maybe would help to make it a little more explicit. There's apparently no one
Oh.
what the negative solution looks like.
Yeah. I mean, that is a question, right? Like the question would be, does this optimal coupling framework give you a way to find examples?
Okay, well,
If you try to think about examples, but
that I can,
I don't actually know.
that I can understand. And that's sort of tied up in the right-hand side of the implication. It says that, well, basically says that there's a. But I don't quite see requires non-CEP.
Oh yeah, because if you use a con-embedding, so if you use a con-embeddable von Neumann algebra, you'll only get this result, right? And this will be bigger. It requires a. Forget about what I said. Okay. This was written confusingly. I'm saying, right? If you take a non-con-embeddable, if you take a con-embeddable von Neumann algebra,
Yeah.
to use for a coupling, then it won't be optimal because the answer you get for the non-con embeddable is smaller.
Went right over my head, I'm sorry.
This is the optimum value. If you choose a con embeddable von Neumann algebra for M, you get something strictly bigger than that, so it's not optimal.
This almost reminds me of a talk that UN gave about his approach to the problem, and it had something to do with inequality.
Well, yeah. So there's many optimization problems. Okay,
Yeah.
but I think I have other topics that I want to get to now. So let's.
At the moment, that for me, one is not like. Wouldn't mind seeing this one more time. So you're assuming that the. Okay, so the idea is you're trying to get a more explicit counter now. That's the idea.
Yeah, I mean that's
Okay.
that's one problem to study, right?
So
that.
then that there's this inequality, there's a strict inequality because that was okay. So it's strict inequality. We get where did the alpha and beta come from then? So this phi is factorizable.
Yeah.
On the left-hand side.
Yeah. So here I'm reversing the steps that I explained before this, which unfortunately were erased.
It's sort of confusing when you have the same location for a factorizable one and the non-factorizable. Anyway, okay.
These are all factorizable though.
Well, not the one on the right-hand side.
Well, okay, this is factorized, so it's in the closure, but in everything in the closure is factorizable through con-embeddable von Neumann algebras.
Right.
As I said, the closure of this is everything which is factorizable through con-embeddable von Neumann algebras. Right, so this is the same thing as factorizable maps through con-embeddable.
As opposed to what? As opposed to factorizable through what? Oh, through finite. No.
This is factorizable through anything. This is factorizable through con-embeddable, which is the same as the closure of factorizable through finite dimensional. Yeah, so everything on this is factorizable maps. So I just write down this phi as factorizable and the other phi is factorizable, right? And then the only difference is.
Have two different phis over there. Why not call them phi1 and phi2?
You can call them V1 and
Well, right,
it's fine.
Well, okay, but I think this is quite. I really like to understand what you're saying, and I still quite. Maybe you can repeat it some other time. We're going back to it again.
Do you want me to call this V1 and V2?
Okay,
This is now alpha 1. Yeah.
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 No.
Yeah, please.
So the top line, in the top inequality, spectrum inequality, that's equivalent to that, you're just rewriting that at the bottom. And that's.
Yeah, right, because as I was saying, right, you take the 2 norm squared and you expand it in terms of the inner product.
Yeah.
And the norm of x and the norm of y are the same, or are determined, right?
Yeah,
So the inner product is the term that makes the difference.
okay, but then where does optimality come in? If you're saying that if the left-hand one, the number 2 one couldn't be optimal, then if it's significantly greater than the other one.
Yes.
Okay. And this is somehow related, where does a more specific example come in to the quantum bay?
Well, we don't have an example yet.
Well,
I mean, but this is saying like this could be a way to try to
okay, well,
think about
it
examples.
looks like you're sort of speeding around the problem. You're speeding around it in an interesting way. I'm sorry, I can't quite take it completely in one sitting. Huh. Okay, thank you.
Yeah. But I mean, just so the idea is like, well, yeah, try to find some weird examples of matrix tuples and try to figure out, how, if you know some example of a von Neumann algebra where you can somehow put these matrix tuples very close together in some way, right? Like there's constructions about von Neumann algebras, like, how to create up projections that add up to a multiple of the identity, like when that's possible, and other things like that, right? If there's some kind of concrete construction like this, which comes from quantum information, maybe that relates to optimal couplings in some way.
Are you suggesting that if you have a countercouple, then there's going to be one that is somehow the more down to earth one, more related, somehow related to optimal benefits?
Yeah. I mean, it's possible. I mean, at the moment, I don't have like a specific concrete example in mind, right? But the idea is like this is just like you study like quantum correlations, you could study optimal couplings as a kind of framework for trying to build examples, right? And I also think that quantum information could be helpful, and that's not something I'm an expert in, but there's many examples in there that may be good to bring into the optimal coupling setting to try to figure out examples. Yeah.
Thank you for this, but I look forward to seeing them again in another setting.
Yes. Okay. So now let's see. How much time do I have? There's. Okay. Okay, so there's many other things that I hope to get to. Maybe I should have just planned to give 4 hours of talks on this topic instead of 2 hours on each, but it's okay.
Seems to me that the series of talks is not to get through it and describe syllabus or curriculum. It's to somehow instill certain ideas. One idea is probably enough. Well, in my experience,
maybe so.
I get happy if I get one idea.
Okay, but anyway, let me attempt to give a couple more ideas.
Fine,
so so here's okay. So again, like I told you before in the first part, we have some kind of space of non-commutative loss. Right, and these are, I have a certain bound R, so I'm always kind of restricted to a compact set as my support in a sense, so I don't have to worry about things at infinity. And so we have this here. And another thing that you could consider is topology on it. So there's weak star topology, which would correspond to, right, since these things are functionals on a polynomial algebra, right? You consider them as So this, sorry, this R is just a positive number.
Sorry,
So this is the radius of the support. So this is just like a plain R, it's not a von Neumann algebra, it's just a number.
okay, but what is the role of R in the definition of these two?
Is that you're considering xj as the operating norm, which is less than or equal to R.
Oh, yeah, okay.
Oh, you're right, this is a little R. Why not? Okay. So there's a weak star topology on this space. Right, but then there's also this Wasserstein distance, which gives you a metric. Now, classical probability, in classical probability, you have that these two give you the same topology. What do you think happens in the non-commutative case? They don't. They don't. Okay, so what happens in the non-commutative case? Yeah, so this thing with respect to Wasserstein distance is not separable. And the reason is essentially the same idea as Ozawa showing that there's uncountably many 2-1 factors that can't embed into each other, namely because there are groups that are hyperbolic, and yeah, so if you have some non-elementary hyperbolic group as a result of Bolshevsky, which also is inspired by Gromov, that you can have uncountably many non-isomorphic quotient groups. And so using this construction, looking at those quotient groups, you can look at the von Neumann algebras of those. You could choose x's based on taking the real and imaginary parts of certain generators, where you have just fixed generators for the master group, and you use the same generators in all the quotients. And then you can get like uncountably many things that are separated in Wasserstein distance. And to get them to be separated in Wasserstein distance, you just want to take a group that has property T to start with, and to make all this work. So anyway, this is not separable, right? And in the weak star topology here, I mean, this thing here will be compact, right? So already this tells us there's something very, very different going on between the weak star topology and Wasserstein distance. If you get a compact space, but then you define a metric on it, and the metric gives you a different topology, and it's not separable. Okay, so that's weird. Yes, because it is compact.
Compact, and well, it's always compact.
Oh yeah. I mean, sure, yeah. I guess it's, yeah. So if it's compact and metrizable, then it will have to be separable. And so, and it is metrizable, right? Because here you're looking at, you can take like a, countably many linear functionals or countably many polynomials to test it on. So, yeah. So
what if we want to play in practical case to get the same result? They're not the same.
yes.
One is still separable, and the other is not.
Yeah. Now I should mention, maybe for the commutative case here, I'm assuming that I'm looking at things supported on a compact set, right? If you have to worry about infinity, they might not give you the same answer. But what I'm saying here in a non-commutative case, the issue is not about what happens at infinity for the distribution, right? You're assuming everything's bounded by R, and these are still wildly different. Okay. And so now here's another factor that I think is very interesting, which is also probably a good idea to mention to you guys, which is that, yeah, so now let's consider some mu in sigma dr. right? And let's say that, let's realize this by a von Neumann algebra generated by X, where X has the distribution of mu. And I will, for simplicity, suppose that A is common embeddable.
Why does it make a difference what the little r is? I mean, can you not just change it and get the same thing?
Well, you can change R, but if you want to consider all the, like, if you want to remove the bound completely,
Okay, well, I'm not suggesting that. As long as you're saying a fixed bound way, you could, since you could just as well say one.
sure, that we can do that.
Okay.
I'm fine with that.
I thought I was a significant variable. Not well, I wasn't really.
Yeah, yeah. If you want to consider all the R's at once, then you have to consider like somehow how these things should patch together globally. But you're just fixing an R. So yeah, you can take R equals 1. I don't care. Anyway, yeah, so now we're taking a law. And so I could ask a finer question about like the topologies agreeing at a point, right? So agreeing at a point, meaning that convergence to mu in the one topology is the same as convergence to mu in the other topology. Yeah, so then the topology, the weak star topology, and the Wasserstein topology agree at mu if and only if the A is immutable.
That's I wasn't expecting that. So you're saying that they're not. You're not saying they're always different, just that they're sometimes different.
So these topologies, yeah, so these topologies agree at points that come from amenable. Yes. Exactly, right? In the commutative case, everything's amenable, and so then this result here actually generalizes that result.
And then suppose that instead of saying agreeing, you said this Wasserstein also separable. Would that be equivalent?
Well, so I'm not sure what it means to be separable at a point. Right, so this is talking about a, yeah.
Well, we agree. Well, you agree at immutable. Why does it mean that topologies agree that?
Yes. So I said this verbally, right? So that would mean that so every neighborhood of mu.
When the classical case, they just pick the same topology overall.
In one topology contains a neighborhood in the other topology.
Okay, so the neighborhood, they have the same neighborhood, or you just say they have the same neighborhood.
Well, so a neighborhood in the one topology is not necessarily an open set in the other topology, but it contains an open set. Yeah.
Just say neighborhood.
Oh, okay. If that yeah. That's
over
fair.
here, well, this is true everywhere. So they have, they have the same topology period in the commutative case, in the classical case.
Yeah.
What is mu? What's special about mu? I've lost. Oh, A in particular actually is sensitive. So and X.
Yeah. So saying that these topologies agree at a point is the same as saying that that point creates an amenable von Neumann algebra.
Is there analogous local statement in the classical case?
Well, in the classical case, the topologies agree, period. So there's not really there's nothing more subtle to say.
It doesn't make sense to say here that the topologies are the same.
So if the topologies agree, if two topologies agree at every single point, then they are the same topology.
Yeah, of course. But,
yeah.
So it's a topology on the set of mu, which is dr It's just
Yeah.
a sigma, that's capital thing.
Anyway, though, yeah, so this is,
And so they're agree everywhere, and only every time you get it.
so what is behind the statement is something like, if you're familiar with Young's theorem that tracial von Neumann algebra is amenable if and only if any two embeddings into an order product are conjugate to each other by unitary.
Okay.
Right, that's the same kind of, it's the same kind of phenomena that are underlying this thing, because saying that so first of all, the Wasserstein distance gives you a stronger topology than the weak star topology, and so the non-trivial direction here is saying that if you have something that converges in weak star topology, then it converges in Wasserstein distance. And something converging in weak star topology is basically some statement like taking the algebra here and embedding it into an ultra product of something. Right. So if you have xn's that are and their non-commutative laws are converging in weak star topology, you could take at the xn's could represent as a sequence could represent an element of an ultra product of the algebras that they live in. And saying that you have convergence in weak star topology will mean that you have a copy of A that's given by this sequence in the ultra product. But then having a convergent Wasserstein distance means that you are able to find some couplings. And so what that would mean is that you can find some other sequence of algebras where you have a copy of X and a copy of Xn that are getting closer and closer together. And so then what that's saying is that if you take the ultra product that you were studying, and then there's some larger algebras such that in the larger ultra product, you actually have a copy of X inside each of the things that you're taking the ultra product of. And so this actually gives you a lifting of the embedding into the ultra product. So essentially, this statement here translates to something like saying that every embedding of A into some ultra product of tracial von Neumann algebras will have a lifting by factorizable completely positive maps. And that lifting property relates to so it's proved by some, let's see, I think by Scott Atkinson and Srivastava.
15 to where? What's it?
Yeah, so I may be out of time, but I guess maybe it takes it writes down some more. All right, so let's say that you have xn and an, and then you have an x that's coming from A. And you want to consider that the non-commutative law of xn converges to the non-commutative law of x in weak star topology. That will mean that so then that will mean that you get a map from A into the ultra product. So let me just say it's converging as n approaches to the ultra filter. Then it converges to the ultra product. You have a map into the ultra product where iota of the x is the sequence of xn's. And then this statement about convergence in Wasserstein distance, right? So convergence in Wasserstein distance means that then you might have, so there exists some Mn where you have a alpha. So A is embedded into Mn and An is embedded into Mn. And the distance between the distance between alpha n of x and beta n of xn goes to 0. And so then what that means is that then you've got so then if you were to consider, okay, the ultra product of ANs as inside the ultra product of MNs, right? So you've got wait, other way that way. This is inside here. You have this embedding into here, and then you also have just the plane product of the MNs, right? Not the ultra product, right? And you have your quotient map here. So then I'm saying, well, if we have this convergence in Wasserstein distance, then the alpha n's are giving us a map here into the plane product. So the lifting is that I have this map here into the ultra product, and then I could have the plane product here and this quotient map, and then there exists a lifting up to here.
Okay. All right.
Yeah. So it's saying, so I mean, there's kind of like a notion of stability, or something like that. And the lifting here is by factorizable maps, and the factorizable maps are exactly the beta n star alpha.
Okay, well, nice pattern. I'm getting some idea of the pattern. I'm afraid I haven't studied anything related to this problem before.
Yeah. Anyway, though, yeah. So the point is, yeah, this Wasserstein distance, right? It might seem like, oh, I'm just trying to do probability stuff. What does this have to do with operator algebras?
Well,
It has a lot to do with it, because making some statement about the Wasserstein distance is saying that you have an embedding of operator algebras and into an ultra product, and that there's lifting. And as you might know, in the classification of C-star algebras recently, people have used a lot of techniques with different types of ultra products, like von Neumann algebraic ultra product, and also ultra product where you use uniform tracial norms and so forth. And part of the questions is, dealing with the difference between these different types of ultra products and kind of lifting properties like this. But here I'm working with von Neumann algebras, right? But here I lifted it here to the actual plane Cartesian product, right? So the plane Cartesian product you can do as a C-star algebra, if you will, and you have this lifting here. Right? And the lifting comes about because with this, if you have convergence in Wasserstein distance, then you have these alpha n's and beta n's, you embed them into a common thing. Right, and so then, if you were to consider the plane product of the MNs, right, I guess I left out, you can take this, and you can map by the beta n star into the plane product of the ANs, and then that maps to this, right? And this commutes because I'm just kind of using these maps and their adjoints, and everything works out.
Okay, well, you wanted to tell us what the takeaway is for Thursday?
Well, Thursday I'm going to talk about something a bit different. Thursday I'm going to talk about something different.
Oh, okay.
But I am going to talk about a lot about this. The weak star topology on the space of laws will come up on Thursday,
Okay.
as well as looking at the L2 distance between things. Now, these are going to be common themes. The topics are going to be somewhat different.
Okay.
Yeah, and so the results I showed today are not really the main theorem of the paper, but they are the theorems which I think have the most connections to other aspects of C-star algebras. So I'm still happy that I got to present these.
Is there any good comments?
Yes.
Trace preserving the maps.
Oh, okay. I was glad you were going to say you found an example of a non-code embeddable von Neumann algebra.
Wish. But there's some examples here if you want to go over them quickly. You could take.
Yeah. So this is the unitary evolution. Okay.
Something called a decoding map or decoding.
Yeah, depolarizing channel.
I just haven't had a book on quantum information theory.
Oh, okay. Yeah. What is this book? And if you want to try to study these from a viewpoint of optimal coupling, I'm happy to work with you on that.
Cool. Yeah, I actually would. It's nothing, I actually.
Ah, okay.
It's a new
Thanks.
book.
Any other questions? Okay, if not, let's thank the organizer.
We should also thank the organizers, I guess.